still on the screen, so we're waiting for. Alex is there.
I'm here. Yes. Can you hear me?
Yes, but we can see Nick's face, so maybe Nick is. You don't want to have your face up. Well, I'm not sure how that works. It's on our side. Okay, so it's our fault. Sorry. Can we put Alex up or not?
I think you should spotlight Alex. Someone has pinned me. Okay.
All right, Alex, you're there. Thanks. Okay, very good. So let's proceed to the second and last talk of this session in the day. And our speaker is Professor Alexandros Beskos at the University College London. Excuse me, at the University College London. So Alex did his PhD back in 2005 at the University of Lancaster with Gareth Roberts and went through various postdoctoral positions at the University of Warwick with Andrew Stewart and Gareth as well, before moving on to a faculty position at the University College London, and included in part of his work was a position at the National University of Singapore. And Alex will be now speaking on manifold MCMC methods for inference and diffusion models. So thank you very much for agreeing to give a talk, and please take it away, Alex.
Okay, thank you very much. Thank you very much for the, for the invitation. Yeah, it would be nice if I could actually be there, but it was not possible. So yes, this is the title of my talk. So this has been a joint work with Matt Graham, that he's now based at UCL. He used to be at he was based in Singapore before that, and with Alex Thierry, that he's still at NUS. So this is this talk I'm going to be giving. It relates with recent progress that it has been out there in Bayesian statistics over the use of Hamiltonian Monte Carlo algorithms. And there have been some paper by Mark Girolami, for instance, and his collaborators on manifold versions of such algorithms. So it is placed within this context. What I'm going to be describing, and I will try to show that as I go, as I present my stuff, is that this diffusion models is an example case of an interesting enough class of models where this manifold MCMC Monte Carlo method can be useful. But in fact, there's a more general context. So for general hierarchical models, one can think about using such a method that I'm going to be describing here. All right, so it's like it's like this diffusion models is like an example scenario essentially, where we found this algorithm to be useful within this scenario. All right, so let's see. So we have I'm in a context of doing parameter inference. So I'm working in the context of Bayesian statistics. So we have a posterior distribution. My model is a stochastic differential equation, a diffusion model, and I'm assuming I have observations at discrete times, capital T. So this capital T here will appear in a number of slides. It will connect, for instance, with computational costs and stuff like that. So let's keep this thing in mind. So that's one thing, and there is this framework. I will call this framework. So, or maybe I should just say that. Even before that, I should say that when I say partial observations, what I mean by that is that first we might have a number of coordinates in our model, in our diffusion model, and we observe a few of them, a fraction of them. So that's one aspect of partial observations. But also I'm adopting here a setting of low frequency observations. So this goes also inside This is also covered by this phrasing of partial observations. So I have low frequency. So my infinitesimal dynamics somehow I can't just use a simple Euler scheme to approximate the transitions from the one observation to the next. So I have to impute some extra. We have to impute some extra positions of the SD in between observations. So low observation, low frequency for the observations, and we allow for the possibility to observe a number of components, not all of them. All right, and this setting has provided statisticians, mathematicians with a nice, rich environment in which to provide a number of contributions. Many work hours have been spent on such a problem since about 20 years ago, and it still goes on. So there are some standard challenges that are around in this setting of low frequency observations. So we have some transition densities that they are intractable, and what I was trying to say before is that they cannot be easily approximated simply by using an Euler scheme or something like that. All right, so one has to do some time discretization, and one has to impute some. All right, so I have a data point at time 1, and at time 2, I cannot just use some transition density approximation to go from time 0 to time 2. I have to introduce some extra. I have to treat this thing as a missing data problem essentially, and I have to introduce some extra variables about where is the position. About the position of this diffusion process of this continuous time model in between 0 and 2. So we have a latent space. This is what I'm saying here, that you can make it as high dimensional as you want, depending on how much imputation one is willing to do. And there are some interesting challenges that arise if one goes down this path, and then there are some parameters, there are some latent variables, dispositions of the SD of the diffusion model that they are not observed. They can have some strange correlations in between them. So the setting, the context is set for an interesting problem in terms of coming up with a nice MCMC algorithm to sample from this high dimensional posterior. That's fantastic. So it gives us a context to work with in terms of coming up with thinking of some clever algorithms and stuff like that. All right, let's see. So the thing I'm going to be describing, so it's an algorithm, yet another approach in such a setting, where this approach will have some particular characteristics. So I find these characteristics to be fairly simple, to be honest. So what we think first is that all right, so let's think of the whole context in terms of a mapping that resembles what we do in our computer. So what we will do in our computer, for instance, to simulate such a model, and this is what this is why I'm referring here to formulating a generative model. So what we will do one would do on a computer is that there will be some simple random variables that they will simulate the model unconditionally, and then through some sort of maps, one could also simulate the data. All right. So I'm assuming here some smoothness on this map. I mean, this map has to be differentiable. So you plug in. I mean, the bottom line is that what I'm saying here is that one samples some extremely simple random variables, and then these random variables they enter a map, and there it is. The observations come out. Okay, out of this map. All right, this map is quite useful. it captures all the structure of the model essentially. Okay, all right. Let's see what's the point of all this stuff. And then the moment we think about this map, at that very moment, we can set up a posterior distribution on a manifold. So we have all these variables that we put inside the map, and this map will give us the data. A priori, these random variables, they have a very simple distribution. I mean, a normal distribution, uniform. I mean, for simplicity, I will assume later in the talk that these variables, they all come from a normal distribution. It makes life easier also because I'm going to be using some Hamiltonian dynamics. So the Gaussian distribution gives some quadratic terms, and the derivative of such terms, they give a linear functions. And the moment we have the data, a mapping of all these random variables has to hit the data, a deterministic mapping of all these extremely simple random variables. It has to be equal to the particular numbers we are given. At that very point, at that exact point, what happens is that we don't simulate data anymore, right? That's extremely easy. We have to take the particular numbers we are given, and we have to simulate these a priori super simple random variables so that they hit the data. There is a very strong condition now placed on these simple random variables. They are not that simple anymore. A posteriori, they are not that simple, so they have to be such so that a deterministic equation is satisfied. This deterministic equation gives rise to the manifold. So I have the prior now. I started with a prior, and then once I look at the data, the support of the prior is restricted to live on a manifold, because a function of my initially simple random variables, a deterministic function, has to hit the data. It has to be equal to something, to some numbers. All right. One can adapt, as I was saying at the beginning of my talk, one can adapt this point of view not just for stochastic differential equations, to be honest. There could be all whatever sort of hierarchical model out there in some Bayesian statistics application, and you can take the same point of view. You can say, right, I have at the bottom of my model, I have a number of variables that they have a simple structure. I can a priori they are super simple, and I can think of the moment I look at the data, I can think of my posterior as being the prior, but now restricted with its support, restricted to live on a manifold. That's it. I mean, one can adapt such a way of thinking for general models out there. It just so happens that this class of diffusion models is quite rich, and it provides a nice setting to work with. All right. Once we have, so this is where the job of a statistician finishes. Okay, so there is this prior, which was simple, nothing fancy. You have densities with respect to the back measure. You see the data, you have manifolders, right? But if you're a statistician, at this point you start worrying. You say, well, what it is that we are doing now? We don't want to work with manifolds. But it so happens that applied mathematicians have looked at such a setting before. So we can sample from a posterior restricted with a support that it lives on a manifold. We can in fact use Hamiltonian Monte Carlo. It's just that there is this extra thing that this extra adjective here, that it makes the method called constrained Hamiltonian Monte Carlo. And people in applied maths, they are aware of they have been developing methods, not necessarily for, not for in a statistics context, not for sampling posterior distributions, but for mostly for sampling physical systems that they follow the Hamiltonian dynamics under some constraints. It's just that in our case, we borrow the developments in this field to use as a sampling tool to sample, to generate samples from a posterior distribution. All right. And then we will have to be a little bit careful. So if people, for instance, have looked at, if some people have looked at this Riemannian manifold paper of Mark Girolami and his colleagues, there are some costs there, some computational costs that arise there, that they can be high relatively to some aspects of something that describes the dimension of the model. In my case, the dimension of the model is captured by this T. So I promised before that this T will reappear in this presentation. Remember, this is the number of times at which we have the number of discrete times at which we observe our continuous time model. So if you are not careful, you will end up with something. If one is not careful, one can end up with computational costs per step that scale cubically with this T, and that's a dead end essentially if something like this happens. So something extra that we have added in these contributions by the applied mathematicians working on constrained Hamiltonian dynamics. All right, we say we have diffusion models. They have some Markovian structure. We can do some blocking that people in statistics working with these kinds of models are quite experienced with. And we can bring computational costs per step down to linear in T, which is pretty much the best one can expect to get. And this is about the computational costs. Something that I should stress here is that there are other methods out there that you can apply an MCMC algorithm for the same problem that they have a computational cost that is linear in T. The nice thing, something I find interesting anyway about the approach I'm describing here is that there is some understanding that it will give superior mixing compared to alternative algorithms. So we can control the computational cost. This algorithm uses information about the curvature, second derivatives of the log posterior, and in a way that computational costs are controlled, and essentially because of the use of a careful use anyway of information of second derivatives of the curvature of the target distribution, we have some expectation that the mixing of the algorithm will be quite good. All right, okay, let's say some things about the model. That's the model. I don't have theta here compared to Nick's talk. So, but you saw an expression of this model before. So that's the drift function A, and Z is so it's not theta, it's Z, my parameter. Tau is my time variable, and B is the diffusion coefficient, W is the Brownian motion, etc., etc. I'm just setting up the notation here. X is the dimension of the process. I can have multivariate processes. W, the dimension of the Brownian motion. I'm allowing for W to be smaller than X. I'm allowing for hypo-ellipticity, for instance. This is the dimension of the parameters, and this is the transition kernel, and I don't have access to that. All right, there are lots and lots of applications out there where people use diffusion process. Essentially, is the standard class of models when you want to work in continuous time and in continuous space in terms of the values that your process can get. All right, so I'm having some examples here. It's the neuronal dynamics, biochemical reaction networks. So the Darren Wilkinson's book, for instance, it describes a lot of, there's a book based on this area of applications. Lots of other stuff. Also in finance, people are using applications, are using models like this, of course. And this is the setting from a statistician point of view. So in this plot here at the top, I'm showing the case of a hypo-elliptic model. So I have the orange thing that it has the roughness of a Brownian motion. So I have this orange path. I'm not observing, I have no observations from this. And then there is this, this smooth component, this blue plot, that I'm only observing this guy at discrete time instances marked by these red circles. Okay. So what my MCMC, what I'm aiming to do is produce an MCMC that it gives me, it takes these numbers corresponding to the red circles, and it gives me everything else involved in the model. It gives me samples from the posterior of the paths that we don't observe here, some posterior of the rough component, posterior of the smooth component in between the observations, and of course, posterior of the model parameters Z. That's the objective here. And this is what I've said before. I allow for the dimension. I allow for the dimension of the. Sorry, here it's the dimension of observations. So indeed, I'm allowing for this guy to be nonlinear, and I don't have to observe all of the components. This relates to this comment on partial observations that I mentioned at the beginning. And here it's deterministic. So I follow an observation regime. I assume an observation regime where the observations, they are a deterministic function of the position of my diffusion model at sometimes separated by capital delta. All right, so this is a new thing introduced, a new symbol introduced in this talk, capital delta. Capital delta is the time in between observations. There will be a small delta also appearing in the next slides. And this would be user specified. So we want to introduce smaller steps in between the actual instances of observations, because delta is meant to be not that small. So we have a low frequency observation segment. This is not restrictive. I could also have noise in the, I could be working with a case that there is noise in the observations. The method I'm going to be describing would be relevant also for that case. Okay, so there are also other classes of models where this approach of setting up a posterior on a manifold, this approach that I'm following here, it's also relevant for other classes of models. And there's a paper by my colleagues and some other collaborator of theirs that they apply these things for inverse problems. All right, let's see. So things will be kept extremely simple. Okay, so I'm just playing around here with the model. This is the directed acyclic graph of the model, nothing more than this. So I have this parameter Z, it affects all the variables of the model. In the circles, I have the variables for the model, and in the rectangles, their distributions. And initially, we have something like this. So we have observations at positions of my diffusion model that they are separated by capital delta. All right, and capital delta is assumed to be not that small. So I have to say something about what happens between time 0 and time delta and times 2 times delta. The transition testing is typically unavailable unless the model is very specific. All right, we have some joint distribution of all the random variables involved here in this graph before we see the data. Okay. All right, that's a prior essentially, and this is where the user starts doing some interventions. So data augmentation. Intervention number one is data augmentation. So we have a low frequency observation regime. Let's turn it into a high frequency one, so that we can actually use some good approximation of transition densities of over small time periods. All right, so the user introduces this small delta here, and suddenly there are many more variables in my model. So the model becomes, the dimension of the model increases. So I have this small delta introduced here, which is the original capital delta that this is given to us by the people collecting the data. So equivalently, this little delta is equivalently specified by this S, this integer S, is the number of imputed points in between observations. So this is the new structure. This is the new graph of my model. So now I have time 0, time delta, little delta, 2 times delta, and then S times little delta, and now I'm arriving at the capital delta. I have to make lots and lots of little steps to reach the time of the first observation. Capital S of them. S, similarly to T, will be appearing in the next slides, and computational costs. We will have to be careful about how S enters the picture in terms of computational costs. So this is where we are. So we have added some extra variables. And now we have the effect of this. Why do we bother doing that? Is because now we can have a good approximations of how we go from the one random variable in terms of the signal, in terms of the diffusion process. If little delta is small, we can have a good approximation. We can assume we have access to good approximations of the transition density. All right, okay, but we pay a penalty for this. There is no free lunch. So the model now becomes high dimensional. Before, the previous graph was showing, the previous model graph was showing capital T random variables plus some constant anyway. But now we have capital T times S random variables. So extra, the dimension increases now. All right, there is some small detail here that maybe people in applied maths, they can come up with numerical approximations of SDEs, for which you can have a way to simulate these numerical approximations, but one might not have access to the transition density. It doesn't matter for the algorithm that I'm going to be showing. I don't really need access to this tilted kappa, to this transition density over small time increments. I need access I need to be able to sample from this thing. All right, I don't need an access to the density itself. I need access to a sampling mechanism. Okay. This is my model. Let's see. Let's step back for a moment and see where we are. Okay. All right. So, for instance, we can have an Euler-Maruyama scheme. So that's it. We generate some Gaussian noise, some standard Gaussian random variables. It's this V here, and we can go from the current position X through this mapping here on the right. We can go to the next position. Okay, that's it. That's the Euler-Maruyama scheme. So let's rewrite. For yet one more time. Let's think of the model. Let's do what is called with the fancy name of non-centering. Let's think of this model in terms of the variables that we simulate. this is exactly what we would do on our computer to actually simulate the positions of the diffusion process. This is what we are doing. So we would get our parameter Z from a distribution mu. We would get our initial position for the diffusion process from a distribution mu. And then we would add the Brownian noise, the noise for the Brownian increments. So V1. So that's the Brownian noise for each small increment for each small step of size little delta, one small step, two small steps, lots of them, S small steps. Here we are at the time of the first observation. Okay, so this is S after S small steps. After two times S small steps, we are at the time of the second observation. After a number of steps, which is T times S, we reach the time of the last observation, the observation of order of 1, 2. So that's the T observation. Okay, this is what we would do on a computer to simulate the path of the realization of the stochastic differential equation of the diffusion process, nothing more than this. And then the data would come along. Okay, let's make our life a little bit easier. Let's express everything in terms of Gaussian random variables. It will be a little bit useful. It's not necessary, but it's useful because I think I mentioned a bit earlier, so I'm going to be using Hamiltonian dynamics. So it's good. Gaussian distributions will give me some nice quadratic terms that will make life easier. So, right, so instead of the original parameter Z, let's say I have some parameter U that comes from a Gaussian distribution. It gets into some map and it gives me Z. Similarly for the initial condition for x0. So I have this V0 that comes from a normal distribution. So what has happened here? So everything now comes from a normal distribution. It gives me, I simulate a bunch of Gaussian variables. I plug them into some functions, and I simulate the sample path. I simulate the realization of the diffusion process. Well, in fact, it's quite simple. I mean, this is how people simulate it. This is how people have simulated sample paths of diffusion processes for ages. So nothing new here. The new thing here is that we have to take under consideration the observations. So all these variables, they have to be such so that they hit the data. A mapping of all these variables has the variables, or let me be precise, the variables have to be such, these singular random variables have to be such so that the mapping of them hits the data. All right, let's be a little bit, let's apply some afferences here. So this is equivalent to the graph I showed before, a bunch of very simple random variables that Gaussian random variables that I simulate on my computer through a map. They would give me the data. All right, everything about the model, the drift, the diffusion coefficient, maybe something that is involved in the observation operator, etc., is inside this mapping GY bar. Everything in the model is inside this guy here. Okay, all right. So, okay, that's what I have done. Nothing too complicated. That's the generative model. This is how we would simulate the data on a computer. But remember, we have to. It's here. The problem is not about simulating data. It's about making sure we hit the particular data we are given. Even more aphoretic. So there's a Q and multivariate Gaussian distribution that through this map that involves everything in the model, it gives me the data. Through a deterministic map, it gives me the data. All right, so this map is going to be extremely important. It's a high dimensional map. So let's spend 30 seconds to think a little bit about this map. So it takes capital T times S plus a constant, all right, what you see here. So as an input, it takes that many random variables. So S, the number of variables I'm imputing in between consecutive observations, in between instances of consecutive observations. And it gives me all the data, y bar are all the data, which are of this dimension, capital T times y, which is the dimension of each observation. And it captures everything, all the information about the model. All right, everything is inside here in this map. That's it. Okay, this is where I'm setting up now a posterior on a manifold. So my initially very simple random variables, these Qs, they have to be now such, their support will be restricted. They have to be initially, they live in this Q-dimensional space. Now they have to be such so that they hit the data through this nonlinear map, this G, Y bar, they have to hit the data. At that very moment, we define a manifold. So there's no way we can work with a Lebesgue measure anymore. So we have to be a little bit careful here. Instead, we will work with the Hausdorff measure. So we have a dimension D. Now the actual dimension of my posterior is D, which is the original dimension of this extremely simple a priori random variables minus y bar, the number of observations. Okay. So there is the ambient space, which is of dimension Q, and the manifold has dimension D. Okay, and using a little bit of manifold theory, in fact, we can write the posterior. We need densities when we want to apply MCMC algorithms. Densities is what will appear within acceptance probabilities and things like this. So we need the density, and the density is using some minimal theory from manifolds is this thing. So it's the posterior pi. It has a density with respect to a Hausdorff measure, which involves this exponential minus phi q, and this is the restriction. So we have to stay on a manifold. Q has to stay on a manifold. And what is this phi? What is this minus negative? What is this minus log density? Well, it's a quadratic term because we express the model in terms of Gaussian, a priori Gaussian random variables. Plus this is where the model is involved. So there are some derivatives of this guy, of this deterministic function. There is this is called the Gram matrix. So the derivatives. So this is a matrix which is the number of observations in terms of rows. So capital T essentially times some constant, and it's capital T times S in terms of columns. Okay, so that's my Gram matrix, high dimensional. I have to be careful about how to get access to this Gram matrix. Something which is interesting here to notice is that we already make use here of first derivatives. All right, so we already have here partial derivatives of this G function. And I have not used the Hamiltonian dynamics yet. So there will be an extra derivative used in the Hamiltonian dynamics. So we will go in two derivatives. So we have information, we will use essentially, it's the same, it's like saying we will use information about the curvature of the posterior. The nice thing here is that usually when one works with two derivatives, with second derivatives, computational costs blow up. The nice something which is interesting here is that this expression here, it's a mapping from something which is it's a scalar map, all right? So it has many random variables inside it, but it gives you a scalar. So finding derivatives of such things is not that expensive. So getting access to second derivatives will happen in a way that the costs are not going to blow up. All right, here we are. And we are done. From the point of view of statistics, we are done. So now we are going to be using constrained Hamiltonian Monte Carlo. People in applied maths, they have known this stuff for ages. So there is this, I think this small superscript here is an error. It shouldn't be there. The one on the gradient of phi. There is this thing called constrained Hamiltonian dynamics. There is a Lagrange multiplier lambda essentially. So and there is also a numerical integrator of such a thing. So for instance, there is something called rattle, which can be used in this case, so that one can come up with leapfrog steps that they are volume preserving, they are symplectic, etc., etc. You can have all the nice properties that they are there in the case of unconstrained of Hamiltonian Monte Carlo dynamics as we know them on regular spaces. All right. Yeah, if I wanted to give a little bit of intuition here, I will not say anything more about this constrained Hamiltonian dynamics. If I want to give a little bit of intuition, you have a manifold. Imagine that your manifold is a sphere. Your current position, currently in your MCMC sampler, you are at some position on the sphere. So what you do is that you give some velocity. You give some velocity to your particle, which is on the manifold at the moment. You have to project. The first thing to do is to project the velocity on the tangent space at the position where you are on the manifold. So then the particle will start moving along the tangent space for each little leapfrog step, and then for each little leapfrog step, one has to project this particle back onto the manifold. Okay. So it takes a direction, the particle. There's nothing that, once you discretize time, there's nothing that will keep the particle on the manifold. So we have to solve a nonlinear equation in high dimensions to project the particle back onto the manifold. It sounds like something that it should be extremely expensive. In fact, it is not, because one explanation I can give for this is that each leapfrog step is local, so you can start your solver for where it is that the projection will live on the manifold. You can start your solver. You can pick a very good initial position for your solver, which is the current position of your leapfrog steps on the manifold. Okay, to the current position to get the next position. All right. So. Yes, that's it. These things can be automated. There's not. If someone wants to use this stuff, there's no reason to program things from scratch. These things can be quite effectively automated. All right, a little bit of discussion on costs. So this is the Gram matrix. In fact, the whole thing is called the Gram matrix, not just one part. So the product of the two matrices. We have to be a little bit careful. This is a T times T matrix, so we have to be a little bit careful. So there is a slide here with costs of finding the derivatives of this function that captures everything in my model. So the bottom line is that, I think I will go just at the bottom. So getting access to the bottom line is that getting access to this matrix is something that scales as t to the power of 3, and that's not satisfying. So that's not good at all. So whatever progress we might do in mixing, we will lose it in computational costs per step. Blocking scheme. This is something that people working, statisticians working on diffusion models are quite familiar with, are good at doing. So, all right, what is this blocking that we can do here? So this is the graph of my model. This is the observation, and I have turned this circle of the position of all of the coordinates of the STE at the time of the second observation. I have turned it into gray color because what I'm going to do, I'm going to condition on all of the values. So I'm running an MCMC, and I'm fixing all of the current values of this guy X at time 2s. All right. That makes life, that very simple, very simple intervention, let's call it like this. It has a huge effect on computational costs, because now the noise is, the Brownian noise is before this, before the second observation. They have no effect whatsoever at what happens after time 2 times 2 multiplied with s. Okay, and at a more high level context, this means that there was this gram matrix that I have there. It inherits now some sparsity, and now life becomes easy. I mean, I don't have to use, this is an example where the block is of size 2. We don't have to use a block of size 2. We can, I think in the next slide, I just use R for the size of the block. And we can do something like this. One has to be a little bit careful so that one doesn't condition all the time on. So these blocks, they have to be, they shouldn't be the same all the time. They have to shift a little bit from MCMC step to MCMC step, so that all of the components of X that are not observed, they have a chance of moving and of being we need to have a chance of having an ergodic Markov chain. All right, this is what I was just saying before. So now it's like I have some pseudo observations, you might call it like this, which make my gram matrix sparse, and the costs now they are not cubic in S, they are not cubic in T anymore. They are linear in S, T, and quadratic in the size of the block now. So that's the effect of what I have done, and that's it. That's the method. I can give some examples in the last 4 or 5 minutes. One is this hypo-elliptic diffusion, which you Nagumo example. It's a hypo-elliptic example. So one can apply this method immediately on this hypo-elliptic SD. So we have some unknown parameters, epsilon, beta, sigma, and the initial condition x0. We only observe the smooth component. This is also the model where this plot I had showed some slides ago comes from. So, all right, this is just used for illustration, just to, there are a little bit of experiments. I mean, this is artificial data. We just simulate the data ourselves. So there is the smooth component at the bottom. We don't observe anything about it. The rough component at the top. Sorry, the rough component at the bottom, the smooth component at the top. So we can use this thing to play around with the algorithm and see if indeed the computational costs for the mixing we expect to get, if it agrees with what we get in practice in this model. We have used the block of size 5. And here we show some results about the computational cost per step of the constrained HMC algorithm as a function of the number of points we impute in between data. And it does scale linearly. And it also scales linearly if we fix S, but instead we increase T, the number of observations, capital T. Also, it scales linearly with this, which is what we would expect. And something which is more interesting is how long it takes to get one effective sample size, one useful sample from the posterior. And this thing also scales linearly with S. It scales a little bit higher with the T. T is the length of the data. So we get something that is suspiciously around 1.25, which agrees with some theory out there that if you want to do HMC in an ideal scenario on D dimensions, you have to pay a cost which scales like D to the power of 5/4. So this is what we seem to be getting here. So yeah, and here there are some plots of the data. That's fine. So that's some conclusions. Why is I think something that one might be wondering is why is that thing irrelevant, and why this? How does this approach compare with alternative approaches that have been proposed out there for doing posterior inference about models that involve diffusions? An argument that I would say here is that the method we presented, it can work with general observation regimes. It can it's a uniform method somehow, so you don't have to change the method depending on whether you have noise in the data, whether you have no noise in the data, which is the case with alternative methods. It is expected, the method is expected to have very good mixing because it uses information from second derivatives of the log posterior. So it uses information about the curvature. So there are things like this that they make this approach interesting. Yes, all right. So this is what I have just said. The rapidly mixing change because we are using two derivatives there in the algorithm, and the computational costs, they scale well with parameters of the model. There's a constant there that it might be a little bit high, but it's a constant. I mean, that's the positive aspect. That's the positive aspect of this algorithm. So, for instance, one example that we have included in the paper is that if you try to run stan, in the case of an SDE model where you have some noise in the observations and the noise is small, you can end up with situations. If you make the noise quite small, you can end up with the situations that if you want to control the acceptance probability, if you want to have a stable leapfrog scheme, you can end up with step sizes of 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, whatever you want. I mean, it can be made arbitrarily, but this approach that I have shown, it scales. It has a scaling of order 1 with respect to the size of the noise in the observation. And there was something else that I want to say. Yes, and it solves some problems actually that I'm not sure from an applied point of view how interesting they are. So you can simulate, for instance, you can reproduce sample paths of whatever bridge you want. So you can have a sphere, for instance, and you can simulate bridges. This observation operator H that I have in the slides, it could be whatever. You can simulate the paths of diffusion condition to hit at time 1 a sphere or something even much more complicated than this, which from my understanding there are no alternatives for doing that. All right, yes, that's it. I will stop here and I have some references. Thank you very much.
Thank you very much, Alex. Do we have some questions from the audience? Please, can we get the, where's the microphone?
Thank you for the talk. I really enjoyed it. I had a question regarding the first part where you constructed the method itself at the very end. I couldn't completely follow you why pi doesn't have a density regarding the Lebesgue measure and why we have to like use the Hausdorff measure.
Yeah, because initially yes, you have some random variables with a distribution that they have a density with respect to Lebesgue, but the moment that these random variables they have to satisfy a condition, a nonlinear. I mean, if this condition here was linear, I mean, you could have something that it would still live on something that it would have a Lebesgue density, but the moment this thing is nonlinear, then you don't have densities with respect to Lebesgue. I mean, you can think of a case that you have random variables x and y, and they are conditioned so that the sum of the squares is equal to 1, for instance, x squared and y squared is equal to 1. So then your support lives on a circle. There's no way you can have a Lebesgue density in such a case.
Thank you.
Thank you.
There's a question. We have.
Hello, thank you for the talk. I just, if I understood correctly, you choose a prior distribution.
Yes.
I mean, well, like, does the method depends on which prior distribution you choose initially?
I mean, I choose a prior distribution in the sense that I start off by saying we are given some particular stochastic differential equation model, some particular diffusion model, which is parametric. So this is the only thing that I need to be given at the beginning. Otherwise, that's it. And there is a model, there is a diffusion model, and there is some. We are also given some way that the observations are connected with this model. So that's it. This is what we are given.
So initially, the parameters have a distribution.
And there's a prior on the parameters, yes, but usually this is the easy part, right? I mean, I think so setting up a prior on the parameters is the easy part. So choosing which diffusion model to start with is probably something that is in application is something that it involves more thinking. Here I'm assuming I'm given the model, I'm given the diffusion model, but that's it, and it's a parametric. It has a parametric form. So I know the drift and I know the diffusion coefficient up to some parameter, up to some unknown parameter. I mean, setting up some priors on the parameters, then it's not hard work. It's one can just select some uninformative priors or things like this.
Thank you.
I think Raul wants to ask a question. If we can just push the mic that way. You don't have to throw it that far.
That's too far. Too dangerous and too far.
Hi, thank you for the nice talk. I have one question. You discussed the scaling with respect to S and T, if I remember correctly. Do you have some intuition when you have to start enlarging the state space of this SDE that you do not observe completely? Does these generative models become more costly? How does this
Okay,
become
if the dimension of the
X of
of
the
the
X?
dimension of X increases.
Yeah.
If one follows the approach that I have showed here, is again is going to be cubic. It's going to be cubic in the dimension of the number of components in X. The hope is that again one can use some sort of blocking again in the same way that I have done here in terms of, so here I have done blocking along the time direction essentially, but people have applied blocking in this type of models, or also along the direction of the components of the diffusion model. So yes, one has to do blocking also along the space direction, let's say. So,
Yes, you have this mapping that goes from the delta W somehow into the data, right? That mapping is going to become more complex.
yes. It will become more complex. I suspect that there is hope. So I think there is some blocking.
Yeah. I just wanted to know the intuition behind the cubic that you mentioned.
The cubic, if one does what I have showed here.
Does this have to do with this mapping or not?
Yeah, with the mapping, yes. I mean, I would be very surprised if it is less than cubic. I mean, this is what I can say, to be honest. I mean, I have not thought about the details, but the first.
Okay. Yeah.
No.
Ευχαριστώ.
Yeah. But I would be extremely surprised if it is. It cannot be more than cubic, but I would be extremely surprised if it is less than cubic. I mean, that's.
Yeah, for sure. No, not less than cubic, but I thought that you were talking about an upper bound. Okay, thank you very much.
Thank you.
That's it. Thank you.
Yeah, sorry, please go ahead, Alex.
No, that's fine. That's it.
Sorry, this is another Alex. Sorry,
Sorry.
there's one more question.
Thank you for your talk. Somewhere at the beginning in motivation, you discuss difficulties which one may face when we build mapping from prior to posterior. Question: what kind of difficulties one can get if one use deep neural network from maybe some work, so maybe you can comment.
I'm not extremely familiar with these things, to be honest. So it might be interesting. It could be that you are describing some interesting direction. Here we have SD models, and from the few things I know about neural networks and stuff like this, I don't see any reason to go down this path here. That's my impression. If you have inverse problems and PDEs and super high dimensional things, maybe.
But do you see here some unresolved problem? You are able to resolve them, but the people who use DNN will face this unresolved problem. Can you imagine that there are some sub problems which are difficult to resolve with DNN?
I'm not sure about this. I mean, there could be. So here it's about SDs. So there could be some SPDs out there where it will make sense maybe to replace some super expensive model other than fluid dynamics or stuff like that. So where Navier-Stokes or where someone could replace the solver of the SPD or of the PD with some neural network and work with this as a proxy of the actual model. So there could be something like that. Here, in what we have done, we are not talking about. So in the example I have showed, this was a two-dimensional stochastic differential equation, and I don't have SPDs in mind or things like that.
Okay, thank you.
Thank you very much.
Okay, so I think there's no more questions. I had one, but I think we're over time already. So let's thank Alex again. Thank you so much.
Thank you very much. Thank you. Thank you very much.
So that concludes this afternoon's session. So we now move to the poster session at 5 o'clock, which is in building 1. I think it's the same location as yesterday's reception. So thanks very much. Thank you. Thanks again, Alex.